we introduced SonicSense, an integrated hardware and software framework to enable acoustic vibration sensing for rich robot object perception. Recent work has leveraged acoustic vibration sensing for object material and category classification, position prediction, estimating the amount and flow of granular material, and collectively performing object spatial reasoning for visual reconstruction. However, previous work focused on a small number of primitive objects with homogeneous material composition, constrained settings for data collection, and single-finger testing. Therefore, it is not clear whether acoustic vibration sensing can be helpful for object perception under noisy and less controlled conditions. We present SonicSense, a holistic design on both hardware and algorithm advancements for object perception through in-hand acoustic vibration sensing. Our robot hand has 4 fingers. A piezoelectric contact microphone is embedded inside each fingertip, and a round counterweight is mounted on the outer shell surface to increase the momentum of the finger motion. Our intuitive mechanical design enables a range of interactive motion primitives for object perception, including tapping, grasping, and shaking motions. The embedded contact microphone is able to collect high-frequency acoustic vibrations created by the contact between object-objects or object-hand interactions. Our robot can infer the geometry and inventory status of various objects inside a container from their unique acoustic vibration signatures during interactions. We derive 12 interpretable features based on traditional acoustic signal processing methods to help distinguish these different acoustic vibration signatures. We performed an unsupervised nonlinear dimensionality reduction with t-SNE on this 12-dimensional feature vector. By shaking the container, our robot can successfully distinguish different numbers of dice or dice with different shapes inside the container. When pouring water inside the bottle held by our robot, we can detect the subtle differences in acoustic signatures based on different existing amounts of water inside the bottle. Our robot can also detect different amounts of water inside the bottle when shaking it. In more challenging object perception tasks, we developed a dataset with 83 diverse real-world objects. Our objects cover 9 material categories and a variety of geometries from simple primitives to complex shapes. Unlike previous work that uses humans to manually hold the robot's hand to interact with objects or design fixed interaction poses and forces for replay, we derive a simple but effective heuristic-based interaction policy to autonomously collect the acoustic vibration response of objects. Our policy works well for all our real-world objects covering variable sizes and geometries. We trained a material classification model that takes in the MEL spectrogram of our collected acoustic vibration signal from the impact sound and learns to predict the material label. The network takes the form of 3 convolutional neural network layers followed by 2 MLP layers. The initial result of our method leads to a 0.523 F1 score. However, we observed object materials are relatively uniform and smooth around local regions. Based on this assumption, we can iteratively refine our prediction. Our final average F1 score reaches to 0.763. Our shape reconstruction model takes the sparse and noisy contact points to generate a dense and complete 3D shape of the object. We stack 2 pointed layers to encode the input and then feed the global feature vector into a decoder network with fully connected layers to produce the final point cloud. Our results obtained an average of 0.0876 meter chamfer distance score. The prediction on objects with primitive shapes generally has near-perfect performance. Additionally, our method exhibits the capability to reconstruct objects with complex shapes only through sparse and noisy contact point estimations. When an object has been interacted with by the robot with its acoustic vibration responses, we aim to have our robot re-identify the object through a set of 15 new tapping interactions. We input 15 both the collection of MEL spectrograms and their associated contact points to the network to predict the label of this object. Among 82 objects in our dataset, our robot can re-identify the same object with more than 92% accuracy. Our robot has a strong resistance against ambient noises and only focuses on vibration signals through physical contact. This ensures high quality and reliable sensing data under challenging environmental conditions. Our entire robot hand costs $215 with commercially available components and 3D printing. Our experimental results demonstrate the versatility and efficacy of our design on varieties of object perception tasks, including solid and liquid object inventory status estimation within containers, material classification, 3D shape reconstruction, and object re-identification. Overall, our method presents unique contributions to tactile perception with acoustic vibrations and opens up new opportunities for future robot designs to build a more robust, complete, versatile, and holistic perceptual model of the world.